So I'm back with the solutions to the homework problems for this section for page 273, 19, 23, and 25. So here is 19A. There's the first part of it. There's the second part. For B, there's all of it. And C, D, 23A is the exact same problem as page 268, number 8. So I just said, see that. After I started writing the quantities down, I'm like, wait a minute, I've seen that before. And you may have realized that too. And here is B. 23C and 24A and B. I apologize, I ran out of room for this, so I kind of continued it along the margin. (25A), 25B and C, and the rest of C. So I will do these problems for you step by step if you had any questions. So starting with page 273, I have to flip in my book here, number 19. So 19A. The question says, a 500 milliliter flask is filled with krypton at STP. How many moles of krypton are present? Calculate the density of krypton at STP. So they're actually asking us two different things. And I don't know why they include this in the ideal gas law part, because you really don't need the ideal gas law per se. I'm going to show you two ways you can do this problem, and it will come out exactly the same. So the first way is you could just convert. You could realize that 500 milliliters, I want to convert to liters. This is krypton. So 1,000 milliliters of krypton is 1 liter of krypton. And once you get it into liters, you know that at STP, 22.4 liters of any gas is 1 mole of that gas. And so when you convert, you would get 0.02 moles of krypton. All of these canceling. And it's one significant digit because these zeros are not significant because there's no decimal point after them. Or you could use the ideal gas law. We can use PV equals nRT, where N equals PV over RT, and I showed you last time how to get that by dividing each side by RT to get N by itself. Now we're at STP, so our pressure is 1 atmosphere. Our volume, 500 milliliters, has to be in liters, but again, we can convert. So we get 0.5 liters, one significant digit there. Our temperature at STP is 273 K, and R, the universal gas constant, is 0.0821 liters, atmospheres over moles times Kelvin. Okay, so we plug in all of our values to our equation. So 1 atmosphere, half a liter, 0.0821, and temperature 273. Now I want to show you why this works out the same way. It's because I'm going to get rid of all my units here. Okay, we multiply 1 times a half and we get a half. When you multiply these two numbers together, it's 22.4. And so you basically just did what you did up here. You divided by 22.4 and you get 0.02 moles. So that is why you can do this either way and come out with the same answer at STP only. The reason we use the ideal gas law is because we can do this at temperatures other than STP and be able to figure these problems out. Okay, now we want to do density. And remember, density equals the molar mass over the molar volume. So for krypton, to find my molar mass, I go to my periodic table and I look it up, and it's 83.80 is what I'm going to round it off to. So 83.8, and I'm going to actually round it off to 8 over 22.4 liters, since I only have 3 significant digits there. So I get 3.74 grams per liter. That's it for the density. Okay, let's go on to B. B says, a weather balloon contains 10 liters of helium at STP. How many moles of helium are present? Calculate the density of helium at STP. I could, again, do this problem the 2 different ways up here. I could do it this way or this way. Just for practice sake, because we are working with the ideal gas law, I'm going to solve it this way using that because they told me to use the ideal gas law and because we just learned about it. So I'm going to use PV equals nRT, where N equals PV over RT. That's a P, not a D. I ran out of my nice paper. Okay, so volume from the problem is 1 liter. Oh, no, it's not. I'm on the wrong problem. Sorry, guys. I'm on B, not C. So pressure is 1 atmosphere. Volume is 10 liters. Temperature is 273 K. And R is, because I have atmospheres in liters, 0.0821 liter atmosphere over mole times Kelvin. And so I'm going to plug these values in. N equals 1 atmosphere times 10 liters over 0.0821 times 273. Canceling out, Now again, I end up with 10.0 over 22.4. And so my answer, I'm just going to write that down here, N equals 0.446 moles. Now they want to know the density. And density, and this is helium. So density is mass over volume. So my molar mass of helium from my periodic table right here, 4.003. So 4.003 divided by 22.4. And I get a value of 0.179 grams per liter. So those are my answers. Sorry I didn't have that. Hopefully you could follow along with my hearing me. Okay, so going on to C. And this is in case you're trying to find this because you skipped over some of the other ones. I believe I'm still on 19. Yep. Okay. Okay, so C. A 1 liter flask is filled with argon by water displacement at 20 degrees Celsius. The atmospheric pressure is 750.6 torr. After correcting for the water vapor in the flask, determine how many moles of argon are present. What is the density of argon at STP? Okay, this is a more complex problem. But again, we're going to be using PV equals nRT. We are going to be using N equals PV over RT. We'll solve for that there. We are given the volume, which is 1 liter. The temperature, 20 degrees Celsius. I better not drop that decimal. Plus 273 is 293 K. Now pressure, they give us 750.6 torr, but this is where we have to remember about our partial pressures. This was gathered over water by water displacement. So we have to use the table found on page 256 of your book. At 20 degrees Celsius, we have to subtract 17.535 torr. 17.535 torr. When we do that, our pressure of just the argon is 733.1 torr. Our R value, because we have liters and torrs here, is 62.36 L times torr over mole times Kelvin. Okay, so now we have the numbers we need to put into our equation. N equals 733.1 times volume, 1 liter. R is 62.36. And T, 293. So canceling out, equals 0.0401 moles. When we do all that canceling, 3 significant digits because I have 3 here. And then they ask us to find the density. And the density, let's see. What gas are we dealing with? Sorry, I have to turn back to my page in my book. So argon. Argon. So argon is right here, 39.95. So density is mass over volume. We can use our molar mass, 39.95 grams, over our molar volume of 22.4 liters. And I get 1.78 grams per liter. So that is 19C. Okay, going on to D. A tank of oxygen gas contains 89 grams of O2. If the volume of the tank is 7.5 liters, what is the pressure of the O2 if the temperature is 21 degrees Celsius? So again, PV equals nRT. This time, they want us to find pressure. So we have to divide each side by the volume. So dividing each side by volume, we get P equals nRT over V. So our N, we're not given moles exactly, but we're given the mass. And we know that if we know the mass, we can figure out the moles. So 89.0 grams of O2. We know O2 is a diatomic, so 2 times 16.00 grams, I get this off my periodic table, of O2 is 1 mole of O2. So I have 2.78 moles of oxygen. My volume is 7.5 liters. Temperature, 21 degrees Celsius. Convert that, becomes 394 Kelvin. And R, because I have liter, well, I'm looking for pressure. I usually just like to use atmosphere, so I'm going to use the value of 0.0821 LATM moles Kelvin. So when you have a choice for pressure, use this value for atmospheres. Just ends up with really kind of nicer numbers, I guess. So pressure equals 2.78 moles times R times our temperature over the volume. Canceling, I'm left with atmospheres. Whoops, this is P out front, not R.
There's a P in here.
Yes, Lydia. Pressure equals 8.9 atmospheres when you multiply these numbers together and divide by 7.5. Okay. Going on. These are